So now we deal with a very important concept, and that is the motion of a charge in a uniform electric field. And this is used in all kinds of technologies, including cathode ray tubes, i.e. old style televisions. This is used in velocity selectors. It's used in spectrometers. All kinds of technologies use this. So this is our first exposure to this, and it is emphasized in both the AP Physics 1 and 2 and the C. So here's the situation. We've got two plates here, and I'm only showing you like just the end of them, so we're kind of looking at it in only two dimensions, but these are charged all the way back into the page, and this is how we can create a uniform field, by having two oppositely charged plates separated by some distance d, and the plates are L long. And what I'm not showing you is all the other lines that go behind these into the page. And you can see at the end we've got these what are called edge effects right here. It isn't quite uniform, but everywhere inside this is pretty much a uniform field. So here's our electron coming in at speed v. It's exactly halfway between the plates, and the question that we're trying to answer here is as follows. Assuming we have a uniform field E for the entire region, if the plates are a distance d apart and L wide, and the electron enters exactly centered between the plates, how quickly does the electron have to be moving? In other words, what's v such that it can get all the way through without crashing into one of the plates? So this is kind of a rudimentary velocity selector. It's only going to let certain speeds v and above through, and we got to solve for what that v is in terms of L, in terms of d, and in terms of the electron charge. And also, we are going to need the electron mass here, which I'm just going to indicate as m of the electron. This has got m of the electron, me. So, as we'll see, this is very much, in fact, it's identical to a projectile motion problem. Now, we got to be careful here, though. What is this electron going to do when it gets inside this field? You might say, oh, the field lines are pointing down. It'll accelerate and follow this kind of path like that, parabolic. But we got to be careful. This is an electron. Those field lines show the direction of force on a positive test charge. Our electron does the exact opposite. It will go like this and follow a parabolic motion like that. But keep in mind, our question is, how fast does it have to be going to make it all the way through? So our limiting case is it enters here, and it will follow a projectile path, but it'll just make it through right there. So that's going to be the path of it. So let's go ahead and set up our equations right here for this, really just similar to a projectile motion problem. What are our givens? Acceleration in the x direction is going to be what? There are no forces in the x direction. It's going to be 0. What is the acceleration in the y direction going to be, though? Well, we do know that it's going to be acceleration y equals net force y over the mass, which happens to be, well, this is an electron, so the force is QE. And this is going to be QE over the mass of the electron. What is the charge of the electron? Well, that's an easy one to remember because we symbolize the charge of the electron with a little e, the elementary charge. So it's E, little e times capital E, over the mass of the electron. That is the vertical acceleration. So now, what else do we know? Well, we know that it's going to fall this distance right here, that it falls, so-called falls, is d over 2. So we know that in our y direction, well, let's go back to our x direction, delta x is just going to be equal to the length. It has to make it all the way through. Delta y is going to be d over 2. There we go. And question is, we're trying to find what v is. So we want to know basically v initial x, and that's going to be the same thing as v final x, which is the same thing as V average x, V bar x. So that's what we're trying to find. This is our unknown. This is what we want right there. How fast is it moving? So what I'm going to do is I'm just going to figure out, we know how far it moves horizontally. My question is, how much time will it take to do that? Time. And we have a couple other givens in the y direction. What is v initial y? Well, that is 0. So let's go ahead and just solve this in the y direction. So we know that we're trying to figure out time. The equation is going to be delta y equals v initial y times t plus 1/2 a y t squared. This goes to 0 because v initial y is 0. So delta y is equal to 1/2 a y t squared, and thus t equals delta y times 2 over a square root. That's our time. I'm going to express this then as what it is. Square root of 2 times delta y is d over 2 over ay, which I already figure out up here, is E times E, electron charge times the electron field strength is the force divided by the electron mass of the electron. So that gives me, quite simply, that the time is equal to the square root of, cancel, d times the mass of the electron over E, little e, charged electron times electric field strength, E. That's the time. So all I need over here, V bar x, is just L, the delta x over t, and that's just equal to, our final result is that it's got to be equal to L over, our time is the square root of dme, mass of the electron, over the elementary charge times the electric field strength. And that's it. This is how fast our electron's got to be moving to make it through without hitting one of the plates. And it will hit the top one if it does.